Right, we're keen to start putting some cable through, but obviously before we pull the cable we've got to know what cable to use. We have to know that the cable is suitable, it can handle the load that's going to be placed upon it. So we need to do some basic cable calculations, and we're doing this because we want to confirm that the cable can operate continuously under full load conditions without being damaged. We want to know that the cable is able to withstand fault currents flowing through the cable. And we want to ensure that the protected devices are effective during an earth fault. And we're ensuring that the supply to the load avoids excessive voltage drops. So we need to calculate what cable size we need to get the power from the MCB to the final load. So the important things are the design current, the actual load, the installation methods, how we put the cable in the building, any correction factors, any stresses on the cable, and the length of the run. Installation methods and correction factors can have a massive effect on the cable. We have to consider each circuit individually and consider any stresses on the cable, any thermal effects, any heating effects. So these are the steps we're going to follow when we're doing our cable calculations. First of all, we need to know how the cable is going to be installed. Is it going to be clip direct? Is it going to be in trunking? Is it going through insulation? Then we need to know our load. What are we actually powering? So we need to calculate the design current. And once we have the design current, we can choose the size of our protected device. Step 4, we need to consider is overload protection required. And step 5, we'll apply any relevant factors to obtain IT. IT is the calculated current capacity of the cable we need, which we get from applying correction factors to either the design current or the rating of the protected device. And once we've got IT, we can move on to step 6. Step 6 is selecting a cable with an effective current carrying capacity. This is where we look through the tables in BS 7671 and choose a cable that can carry the tabulated current. This will be our IZ, and this will be our final choice of cable. And just to make sure, in step 7 we do a volt drop test, and this will confirm that the cable is satisfactory. We're going to go through this in a lot of detail. That's just a quick overview. When we're doing our cable calculations, we've got lots of different symbols for the value of I. We've got IB, which is the design current of the circuit, what the actual circuit is going to be pulling. We've got IN, which is the rated current of the protective device. That's the actual number printed on the MCB. We've got IT, which is the tabulated current after correction factors have been applied. This is the suggested current after we've thought about the stresses the cable might be under. IZ is the current carrying capacity of the cable. This is the actual cable we're going to be using, the size of cable. And I2 is the actual tripping time of the protected device. Not its rated number, what's printed on the device. This is the actual value where the device will trip. We've got voltage drop as well, which we need in our calculations, which is the decrease of electrical potential, how much voltage is lost when it's going down the cable. We have to make sure that the values are in the right order. IN, the rated current of the device, is not less than IB, the design current. And IN, the rated current of the device, must not exceed IZ, the current carrying capacity of the cable. So we have the coordination formula. IB is less than or equal to IN, which is less than or equal to IZ. So basically we want the numbers to increase. IB being the lowest, 13 amps, that's our current that's going to be used. And that's got to be less than the rating of the MCB, otherwise this MCB will keep on tripping. If this MCB was rated for 6 amps and the design current is 13 amps, it's going to constantly keep tripping. And the cable has to have a greater current carrying capacity than the rating of the protective device. Table H2.1 in the on-site guide gives us some advice on maximum floor area served for our circuits. These are standard circuit arrangements for rings or radials. And if we look at table 7.1, also in the on-site guide, that gives us maximum lengths for various different circuits. It has the protected device, the cable size, allowed installation methods, and then the various lengths. Quite a complicated table to work your way through. And we also have in BS 7671, appendix 15, we have information on rings and radial final circuit arrangements. That gives out the layout of circuits, also the size as well. I'm not a massive fan of using the floor area. It gives you an indication, but I prefer to know the actual amount of cable I've put in. So just so you get a sense of scale, I put the area of 100 square metres on this football pitch, along with the 3-bedroom house. We're not going to have very long cable runs, but it is possible to exceed the various lengths and end up with an unsatisfactory volt drop or a ZS that's too high. Floor area can easily be exceeded, because don't forget you've got to consider the cable going to the fuse board as well, and also the amount of cable going to each socket. You can do some preliminary steps with your voltage drop to check that your cable is going to be suitable, and you can also do that with your ZS. The current carrying capacity tables we use when we're doing our calculations also give us our maximum volt drops in this column here, and this is the voltage drop per amp per metre of cable. And so we can use this to help determine the maximum length of runs that we can have. And if we know the design current and the length of the run, we can do a preliminary check to make sure that the cable we're thinking of using will be suitable. In this example, it's a radial circuit for sockets. It's 25 metres. The protective device is a 20 amp MCB. But we need to know the design current. And being a socket circuit, we don't know what the design current's going to be because it depends what people plug in. The on-site guide does give us some guidance on presumed loads for circuits, but generally with the socket circuit I like to go with the protected device, so you can't undersize the cable. We'll go through this a little bit more further into the video. So in this example, my design current is going to be the rating of the protected device, which is 20 amps. So we know that the maximum volt drop permitted is 5% of 230 volts, which is 11.5 volts. So we can use that 11.5 volts to calculate the voltage drop factor. So we divide the millivolts by the design current times the length of the run, and we get a volt drop factor of 23. So we can look up this factor in our tables, and anything more than this is unsuitable. So in the volt drop table, we can look at our factor of 23, and anything less than that is a suitable cable for us to use, and anything more is not. So we can rule out 1 and 1.5mm squared cable because the voltage drop factor is higher. And so we need something less than 23. And 2.5 is 18. So for this particular set of circumstances, 2.5mm squared cable looks like it's going to be appropriate. But obviously we have to apply other correction factors as well. This is just a preliminary check to see if a cable might be suitable. And we can get an idea of the maximum length of the circuit if we transpose the volt drop formula. So we'll divide the maximum volt drop in milliamps by the voltage drop factor times the design current, and that will give us a length for the circuit. And anytime you transpose the formula, I always find it useful to put the answer back into the original formula. And we can check it. 18 times 20 times 31.94, which was the length we calculated. Divide that by 1,000, and we get back to 11.49. And we're back to our maximum volt drop. We've got 11.49. We've lost a little bit in the sums. And if we know our ZE, we could use our maximum ZS to get an idea of the maximum length as well. When we do our measurements, such as R1 plus R2, we'll be doing those when the cable is cool at ambient temperature. But in the design stage, we need to consider what the maximum resistances would be when they're at maximum operating temperature, which is 70 degrees C for twin and earth cable. The maximum ZS in BS7671 is at maximum temperature. So we need to use a correction factor on our R1 plus R2 to raise that to maximum operating temperature as well. So this is the formula to find the length. This is the ZE at maximum. So the ZE is 0.35, the ZS is 2.19. So we take away the ZE from the ZS, and that gives us 1.84. And then the R1 plus R2 value, which is 19.51 milliamps per metre, that's in the on-site guide. We need to times that by 1.2 to raise that to maximum operating temperature. We times that by 1,000 to get the milliamps per metre into metres, and we get a length of 78.59 metres. So we've done the volt drop test and the ZE test for maximum lengths, and we've got vastly different maximum lengths. The volt drop gives us nearly 32 metres, and the maximum ZS 78 metres. Why the disparity? When you're doing everything at maximum, you're not going to really get accurate lengths. I mean, take the volt drop for example. We're saying that our design current is 20 amps. The design current might be a lot less than 20 amps, which will increase the length of the run. We're also going with a high ZE and a maximum ZS. And we don't design everything to the maximums. You don't design a circuit, so you get 2.19 ohms. This is just giving us an example of possible lengths of circuit we could use in our designs. You don't want to run cable and then work out that it's too long. You want to find out these limitations on paper first before you start installing cable. Just because the maximum ZS might suggest a longer cable run, the actual voltage drop on that cable would not be satisfactory. And again, this is just giving you an approximation of the length of run it's possible to have. It helps in the design stage because you can design to this information. You know roughly what area you're working in lengthwise for your cables. So I'm certainly not suggesting that we design to the maximum allowed. We want to keep things like ZS as low as possible. This is just to show that they are maximum allowances. And if you're reaching maximum permitted values, you might want to consider using a larger cable cross-sectional area, or have different installation methods, or see if the cable could be run in such a way where you don't need so many correction factors. So it's useful to know the cable's limitations. Okay, we're going to use these steps here to calculate the size of cable that we need, and then to confirm that it's suitable. What do we know about the circuit we're designing? We know it's a radial circuit. It's got a 3 kilowatt load, 3000 watts, and that's a fixed load. It's a dedicated circuit. It's in flat twin and earth cable. The length of the run is around 10 meters. Clip direct. We've got a little bit in trunking and a little bit plastered in the wall. So from tables 482, we have cable in trunking, we have cable clip direct, and we have cable in masonry. Masonry and clip direct are method C, and a little bit in trunking is method B. Method B has a greater effect on the cable than method C, so we'll choose method B as our installation method. So first off, we have to calculate the design current, the current that the appliance is going to use. And in this case, it's really simple because it's a fixed load. It's a 3 kilowatt load, so we have to convert that into watts, so that'll be 3000 watts, and we divide that by the voltage. The voltage is given at 230, so 3000 divided by 230 gives you 13.04. So our design current is 13.04 amps. Now that we have the design current, we can work out what size of protective device we need. This is the rated current of the protective device, known as IN. The rated current is the number printed on the actual device. We know that we're going to be using RCBO, and the common sizes for them are 6, 10, 16, 20, 25, 32, 40 and 50. So in the formula, design current has to be less than or equal to IN. Or you could put that the other way around and say IN is greater or equal to the design current. We've got just over 13 amp design current. The nearest MCB size, which is greater than 13, is 16. So we'll go for the 16 amp. 16 amp RCBO. And we've got the correct sizing. IB is less than or equal to IN, the rating of the protective device. Is overload protection required? Appendix 4 base 7671 gives us various equations. So we have equation 1, which is for a single circuit. Equation 2, which is for groups. Equation 3, which is for groups not liable to be simultaneously overloaded. And equation 5 is when overload protection is not required. We apply factors to compensate for the negative effect each factor can have on the cable. All of these factors could potentially limit the cable's ability to lose its heat, and every cable's got a maximum temperature to which it can operate. And in the case of twin and earth, what we're using, that maximum temperature is 70 degrees. So we need to make sure that this cable can dissipate any heat. A cable surrounded by thermal insulation, that is going to prevent heat leaving that cable. And if the ambient temperature is high, that will have an effect on the cable. It's starting off at a warmer temperature. If it's buried in the ground, that's going to have an effect. Some effects are positive, some effects are negative. And if cables are grouped together, that grouping has a detrimental effect. It causes the cables to warm up. And so we apply factors to compensate for the stresses on the cable. So we can use equation 5, overload protection is not required. That might sound a little bit odd, but we'll talk a bit through that later. Here we divide our design current by the relevant factors. If you haven't got any factors, you can just times it as 1, or you could just leave them out. So in this very simple example, we haven't got any correction factors, so therefore our IT is our design current, which is 13.04 amps. So we're looking at the correct table for twinning earth. There's a couple of tables we can use for twinning earth. In this case, I'm going to use table 4D2A. If we want to see which cable can carry 13.04 amps. So we make sure we got the correct table. Multi-core 7°C thermoplastic insulated and thermoplastic sheath cables, non-armoured, copper conductors. That's all good. And we want to choose reference method B, and it's a 1 2-core cable in a single phase. And then we can look down the column 4 and see which cable we need. We needed a cable that can carry 13.04 amps. Oh, 1 mil's 13 amps. That's a tiny little bit under the 13.04 amps that we need. Is that 0.4 that much of a bother? Let's have a quick look at this table though. Minimum cross-sectional area of conductors. And it tells us a power circuit, because this is a power circuit, it's not a lighting circuit. The minimum cross-sectional area for a power circuit in copper is 1.5 millimeters squared. So that 1 millimeter is out, thankfully. The next value after 13 in column 4 is 16.5 amps, and that would be a 1.5 millimeter squared cable. So power circuits have to be at least 1.5 millimeter squared cable, and 16.5 amps is greater than 13.04 amps, so that looks like a good choice of cable. So 1.5 millimeter squared twin earth cable installed in method B has a current carrying capacity of 16.5 amps, so therefore we have our IZ. You can see by the table how installation methods affect the current carrying capacity of the cable. If it was clip direct, the 1.5mm cable could carry 19.5 amps. When we put it into trunking, that 1.5 twin earth CCC comes down to 16.5 amps. The fact that the cables are closed means that the cable can't lose its heat as easily as it can if it's clip direct. So it's down rated to 16.5 amps. So this is why it's important to know your installation methods when you're doing your cable calculations. The next thing that we need to do to confirm that the cable is suitable and it's not too long, for example, is check the volt drop. And we use this formula here. Volt drop equals millivolts per amp per meter times the design current times the length, and we divide that by 1000 to get it from millivolts to volts. So we know the design current, 13.04 amps. We know the length, 10 meters. But what's the millivolt per amps per meter? Where do we get that? We get it here. Table 4D2B will give us our millivolt per amps per meter, and for a 1.5 millimeter squared cable, that is a value of 29. So it's 29 millivolts per amps per meter. So it's some simple math. 29 times 13.04 times 10 divided by 1000 gives us our volt drop of 3.78 volts. Now, is that value acceptable? We're taking that our voltage is 230 volts. In lighting circuits, you're allowed 3% volt drop, and other uses, it's 5%. 5% of 230 is 11.5 volts. So therefore, 3.78 volts is well under 11.5 volts. So our volt drop for this cable is acceptable. So to recap, we decided on our installation methods, then we worked out our design current, and from our design current we could work out our rated current or the protective device. From that we can work out our tabulated current. In this case we've got no correction factors applied. Then we can look at the various tables to work out our current carrying capacity. In this case it was a 1.5mm squared twin earth cable which can carry 16.5 amps. And our volt drop was 3.78 volts. So 1.5mm cable appears to be acceptable. for these particular set of circumstances. We've got a relatively low design current, a very short run, and there's no correction factors on the cable, so the cable doesn't need to be derated. So in this circumstance, a 1.5mm cable appears to be acceptable. You can get online cable calculators and you can check your results against these. So let's have a look. We've got a domestic twin earth cable. It's in conduit or on the wall. The voltage is 230. The load was 3 kilowatts. The volt drop is 5%. Non-lighting circuit. The length was 10 meters. Let's calculate minimum cable size. So there we go. It's telling us the minimum cable size for this particular set of circumstances is 1.5mm squared with a volt drop of 3.8 volts. There's your load, 13.04 amps. So they're quite useful just to check your figures, but don't use them as your main tool to calculate cable size because they often only have basic settings. They don't have the full range of correction factors or installation methods. So it's best to work it out yourself. Let's see what happens if we increase the length of this circuit. Now, if we keep everything the same design current, the same IN, the same IT, the same IZ, but we've increased the length of the run to 35 meters and do our volt drop calculation, we'll find that now this cable isn't suitable. The cable is too long. The volt drop is 16.24 volts when it's got to be 11.5 maximum. So the length of a run has been a factor in our cable choice. We have to go up to the next size, which will be 2.5mm square cable. This is where the preliminary step comes in useful, we mentioned earlier on. It saves going through all the calculations, then getting to the volt drop and finding it's not suitable. So we divide our maximum volt drop in millivolts by the design current times the length, and that gives us a factor of 25.19. So anything higher than 25.19 will be an unsuitable cable. We need to go for something less. So bearing that in mind, let's have a look at the same circuit with some correction factors. So we're using twin earth cable. It's 35 meters. We're clip direct. But in one section the cable's grouped. We've got 3 circuits together. Also in the cupboard where the heater is, we've got an ambient temperature of 40 degrees C. Let's calculate the cable for this circuit. So the design current and the protected device are still the same, it's the same circuit. But this time we've got some correction factors, so we need to calculate our IT. So we take our design current of 13.04 amps, and we've got the grouping, 3 cables. We'll find that in table 4C1. So we've got a correction factor of 0.79 for the grouping, and the ambient temperature, we've got a correction factor of 0.87. That's table 4B1. Now you'll notice I've only got the one factor here, 0.79. If the grouping and the ambient temperature were in the same place in the same location, we'd combine the 2 factors. But because the grouping is in the consuming unit cupboard and the ambient temperature is in the cupboard where the immersion heater is, they're 2 separate locations. So we don't combine the correction factors. We just select the correction factor that derates the cable the most, the lower number. 0.79 is lower than 0.87, so that's the correction factor that we use. So we look in table 4D2A, that is going to suggest to us a 1.5mm square cable. But we've done our preliminary check on the volt drop. We know that we have to have a volt drop of 25.19 or less. 1.5mm square cable is 29. So we have to go to 2.5 cable, which is 18 millivolts per amps per meter. So our IZ will be 27 amps on a 2.5mm squared cable. Our volt drop will be 18 times 13.04 times 35 divided by 1000, which will give us our volt drop of 8.21 volts, which is below the 11.5 volts maximum. So this cable is good. Generally though, I think most electricians would use 2.5mm square cable for an immersion heater on a 16 amp or a 20 amp MCB. You've got a bit of redundancy in your cable. You're not designing everything to the edge and you know you're going to have a decent volt drop. I also think it's a legacy of the BS3 or 3.6 fuse, where it wasn't permitted to use 1.5mm square cable on a 15A fuse, and I still think that plays a part in people's thinking now. There's also the correction factor of 0.725 for your BS3036 fuse, and that correction factor generally meant you had to use a cable with a larger current carrying capacity. You also have the standard circuit design as well, the 20A MCB on a 2.5mm square cable. So I think all these factors generally nudge people to use a 2.5mm square cable, but even then, you can't presume that 2.5mm squared is going to be acceptable, because if you do the calculation for going through insulation, that might derate it so much that 2.5 won't be acceptable. You're going to have to go up to the next size, 4mm. So we do have standard circuit designs, but you've still got to check them against your installation conditions. Volt drop will vary depending on the circuit. If you've got a single circuit like an immersion heater, which is a fixed load on a particular length of run, you'll get a value for volt drop. If you look at this socket circuit here, for example, and you can see how the total volt drop for the circuit changes depending where the load is. If the highest load is at the farthest end, that circuit will have a larger volt drop. If you've got a 3A load at the beginning of the circuit and a 13A load at the end of the circuit, we've got a total volt drop of 4.5 volts. But if we reverse that situation, we have a total volt drop of 1.26 volts. So you might think, for example, I know this doesn't apply to domestic, but if you've got like a long corridor and you know that heavy loads aren't going to be placed on that, it's only used for cleaners' hoovers and such, this circuit can be longer. You've got to consider how the circuit will be used. Obviously, a kitchen is very different to a circuit supplying power to bedrooms. The kitchen's going to use a lot more power, so the volt drop will be greater. And so you can actually calculate the volt drop in each leg of the circuit, and that might give you some leeway in your length of circuit you can use. But as you can see, it's the design current and the length that really affect volt drop and the position where that load is on the circuit. We'll do a couple more examples, but I just want to mention how the methods of installation can affect the current carrying capacity of the cable. In a domestic rewire, the vast majority of the cable you're going to use is flat twin and earth cable. So let's just have a look at some installation methods and how this can affect the cable. Table 482 gives us various installation methods for flat twin and earth cable in thermal insulation. This is either in stud walls or above plasterboard ceilings when you've got insulation laid on the top. And you've got methods 100, 101, 102 and 103. Method 103 is the most detrimental on cable because the cable is completely enclosed. The other methods, it's either touching the plasterboard ceiling or the plasterboard stud wall, or it's clipped to a joist. It's all about the cable being able to lose its heat, and if it's completely enclosed in insulation, the cable finds it harder to lose that heat. Let's have a look at the corresponding current carrying capacity table to see the effect these installation methods have on the current carrying capacity of the cable. So we can see in table 4D5, if we look at reference method C, clip direct often gives us the highest current carrying capacity for conductors. And as you can see when we look through the methods, how that current carrying capacity decreases. So let's have a look at 2.5mm squared cable. Clip direct, it can carry 27 amps. Method 100, it's down to 21 amps. Method 101, 17 amps. Method 102, 21 amps. And method 103, it's down to 13.5 amps. Basically, it's been derated by a half, and that's because the cable is completely enclosed in insulation. So when you're planning your cable runs, one thing you make sure you don't do is have any twin and earth cable going through thermal insulation. That can make your design impractical or impossible. An example being your ring final circuit wired in 2.5mm squared cable. That wouldn't be acceptable in methods 101 and 103. You'd have to find a different way of installing your cable. Because those methods derate the cable to either 17 amps or 13.5 amps, in a ring final circuit, the cable's got to have an IZ of at least 20 amps. Obviously, you consider this before you start running your cable. You don't think about this after your cable's been run and installed. The problem is, though, building regs often demand that thermal insulation is installed in stud walls and in ceiling voids and wherever. So good planning of your cable routes is very important because there will be insulation around, and we have to work with that and deal with that It's all very well saying avoid it, but sometimes it's impossible to. And it's important to work with any other builders or installers. Often as electricians, where we're in the cable, you have builders building the stud walls and partitions and whatever. We're going to install our cables when the stud wall's empty, but further down the line, somebody's going to come in and fill that stud wall with some form of insulation. So it's important that we work with other trades, and our cable calculations do take into account any future insulation that might be added. So if you go into insulation, you might want to think about installing it so it's reference method 100, for example. It's not so onerous on the cable, but then we have the problem that we're moving the cable away from the centre of the joist where we like it because it's nice and protected. We're moving it to the edge, touching the plasterboard wall, and there's a possibility that when the plasterboard gets put on, somebody puts a screw through it. So insulation can cause real problems on a practical level, installation-wise, and also with its thermal issues. So real good care needs to be taken when you're installing a cable in stud walls. But anyway, let's get back to some cable calculations. So let's consider an electric shower. It's 8 kilowatts. The cable's clip direct, twin and earth clip direct. The length of the run is 25 meters. The cable travels through 100 millimeters of insulation. So first of all, we work out the design current. 8,000 watts divided by 230 volts gives us a design current of 34.8 amps. And then we can choose our protected device. We need a protected device that can handle 34.8 amps. So we need to go higher than that, and that would be 40 amps. So our IN is 40 amps. Then we need to know, can this circuit be overloaded? Well, it's a fixed load. It's an 8 kilowatt load. It could pull less, but it's not going to pull more than 8 kilowatts. So we've got a fixed load. It can't be overloaded. So we can use IB to calculate our IT. But we do have some correction factors. We've got an ambient temperature of 35 degrees C. So we need to add that correction factor to our calculation to get IT. Table 4B1 gives us our rating factors for ambient air temperature. And for twin and earth cable, which is 70 degree thermoplastic cable, in an ambient temperature of 35 degrees C, the correction factor is 0.94. We've also got another correction factor. The cable goes up to the loft for a short while, and it goes through 100 millimeters of insulation. So we need to add the correction factor for that. So we use table 52.2, and the correction factor for 100 millimeters of insulation is 0.78. So we add that to our formula as well. We're combining these two correction factors because they exist at the same time. It's 35 degrees in the loft and the insulation's in the loft as well. So we have to combine the two correction factors. So 0.94 times 0.78 gives us a new correction factor of 0.73. And if we divide 34.8 amps by 0.73, we get a tabulated current of 47.6 amps. Right, now we need to find out our IZ. This is the actual cable we're going to install. So we need to look in the right tables. There's a couple of tables that we can use. Table 4D5 is specific to cables in stud walls or above plasterboard ceilings covered in insulation. We're slightly different in this example because we're going through 100 millimeters worth of insulation. So we're going to use table 4D2A. And if you look down the correct column, method C, reference method C, and our IT is 47.6 amps. We look down, 6 mils 46 amps, so that's no good. We have to go up to 10 mil cable, which is 63 amps. So our IZ will be a 10 mil cable with a current carrying capacity of 63 amps. And the fact that it's gone to 100 millimeters of insulation has increased the size of the cable we need quite dramatically. This is why it makes sense to try and get your cables from A to B without going through insulation. But like we've said, sometimes you just can't do that. You've just got to make sure that you take into account any correction factors, and then you know that your cable choice is good. So the next step is to work out the volt drop and see if that's acceptable. And we look at table 4D2B, and we look at 10 millimeter squared cable, and it gives it a millivolt per amp per meter value of 4.4. And we have our design current, and we know the length, so we can now calculate the volt drop. So 4.4 times 34.8 times 25 is 3,000 828. We need to convert that from millivolts to volts. So we divide by 1000. And as we recall, the maximum volt drop is 5%. And the volt drop is 3.82, which is below the maximum of 11.5 volts. So this cable looks good. So we have good coordination. The design current is less than the rating of the protected device, and the protected device is less than the current carrying capacity of the cable. Let's clear out some of the numbers. We'll keep the design current because that's not going to change. We'll keep the IN because that's the same. Let's have a look at this if we're using reference method 103 and table 4D5. This is for a cable totally enclosed insulation in a stud wall. Let's do the maths for this. So CI, we would class that as 1. We're not using the correction factor for CI because we're actually going to use table 4D5. We'll still use the correction factor for ambient temperature, 0.94. So the mass would be 34.8 divided by 1 times 0.94, and that would give us 37.02 amps. So in table 4D5, we need to look up 37.02 amps and see which cable can carry that current. And as you can see, method 103, the only cable we can use is a 16mm squared cable which can carry 42.5 amps. Now 16mm squared cable, that's a hefty cable, but the problem is actually terminating it. You generally have some isolation for electric showers. It's often a pull cord on the ceiling, and getting a 16mm cable into a back box is just not practical. The termination has got to be so difficult, it could actually become a risk in itself. Sometimes you just have to think of a different way of doing things. So you can see there in the first example on the shower circuit, the IT was 47.6 amps and the suggested IZ was a 10mm squared cable. In the second example, the IT was 37.02 amps, which is less than the 42.6 amps of the previous example, but the IZ required a 16mm squared cable, so it shows the importance of using the right table and using the right correction factors. I mentioned earlier there's an equation where overload protection is not required. That might sound a bit odd. It refers to a circuit with a fixed load, such as a shower. Now that shower can only pull its kilowatt rating, so if it's 8,000 watts, the amount of current that the shower will pull is fixed. It could pull less, but it can't pull more. So the coordination between the protected device and the cable can be different. So the protected device doesn't have to offer overload protection. We still have to provide short circuit protection though. An MCB has 2 tripping mechanisms. It's got a magnetic trip and a thermal trip. The magnetic trip would deal with the short circuit currents, and the thermal tripping mechanism will deal with the overload currents. The current that will cause instantaneous tripping of an MCB is generally between 3 to 5 times its rated current, but an MCB won't trip on 32 amps. We have the operating current of the protected device, known as the I2. For an MCB, that's generally 1.45 times the rated current, so that will be 46.4 amps for a 32 amp MCB. But we can look at the actual time curve graphs and we can see how much current will flow to make the MCB start thinking about tripping and how much current will flow for the MCB definitely to trip. This is a time curve standard for the 60898 MCB, and there's various different tests. These are factory tests, not tests we carry out. We can't carry out these high current tests on MCBs because it would be too dangerous. And there's various different tests. They have a test at 1.13 times IN, and the MCB should not trip in over an hour. And then they have the 1.45 times IN, and the MCB should trip in less than an hour. The instantaneous tripping characteristics for a type B is 3 to 5 times IN. Type C, it's 5 to 10. Type D, it's 10 to 20 times IN. This is a time curve graph for Wilex MCBs, but I believe all MCBs have to operate within these timescales. So as you can see, a 32 amp MCB can carry 36.16 amps, and it should do that for over an hour. So it doesn't trip on slight overload. the current increases to 1.45 times 32 amps, which is 46.4 amps, it's got to trip in less than an hour. So the cable also needs to be able to take an overload for a short period of time. That's why I don't like to design everything right on the edge. I like to have a little bit of capacity in your cable design. And BS7671 has the time curve graphs for MCBs, rewirable fuses, BS88 type fuses, so you can get your disconnection times. Of course, it goes to show how important the ZS reading is, because if you've got a poor ZS, you won't be getting these currents and you won't be getting these tripping times. The often cited example of leaving out overload protection is electric magnets, where an overload could cause the failure of the magnet, the dropping of a heavy weight, and they'll have systems in place. They'll have alarms and warnings and battery backup sometimes, so power can't be lost. In domestic, we can't leave out overload protection really because we're using MCBs, and as we mentioned, overload protection is built into the MCB. But what it does mean is that you can use the fact that overload protection is not required when you're doing your cable calculations. And sometimes being able to use the design code rather than the rating of the device can give you more options in your cable calculations. Because we know the precise nature of this load, it's 8,000 watts or 34.8 amps. This cable can be overloaded if they're rated correctly, of course. So if we do an IT calculation with the design current, 34.8 amps, we've got a correction factor of 0.94. That's for ambient temperature being 35 degrees rather than 30. We do the sums and it gives us an IT of 37.02 amps. And you can see we do the same with the IN, which is 40 amps. 40 divided by 0.94 gives you 42.55 amps. So you can see how your tabulated current can change. Because your tabulated current changes, that will also affect your IZ. So when you look for your cable size, you might be able to use a smaller cable. The design current is still 34.8 amps. This corrected value of IT, 37.02 amps, it doesn't mean that 37.02 amps is being pulled. It means that cable is being heated as if it had 37.02 amps flowing through it. So we size our cable to accommodate that additional heat. When it says overload protection is not required, it's not saying that you can leave the MCB out, because we still have to provide full protection. Overload protection will be there. It's not like we're taking a section of the MCB out, so we're losing overload protection. It's more to do with coordination. So as the regs tell us, where the overcurrent device is intended to afford fault current protection only, IN can be greater than IZ, and I2 can be greater than 1.45 times IZ, but the protected device must be selected for compliance with regulation 434.52. This is basically saying that the protected device should operate within a time where the permitted limiting temperature of any conductor or cable has not been exceeded. Your cable calculations are very much based on the maths. You've also got to consider the nature of the load. An electric shower, that's on for what, 5-10 minutes? Let's have a look. So people will spend about 7 or 8 minutes in the shower. Makes a big difference. The cable's got a chance to cool down. But when charging your car, that can be 8 hours. So I think that's got to be part of your design considerations when you're thinking about what size of cable to install. We've obviously got to go with the maths, but you need to use your judgment as well. Because cable calculations could suggest a cable which is technically suitable, but when you consider the load characteristics, you might think some more capacity is needed. Something to consider is overload and diversity. We've been concentrating on one fixed load, such as a shower or an immersion. When you've got multiple elements, you have to consider the fact that one of the elements might fail on, and that could cause an overload situation. An oven and hob have got lots of elements. You've got the hob elements, and you've got the various oven elements. Say, for example, you had a 13.5 kilowatt oven, that would be 58.69 amps. Because of the nature of ovens where the elements heat up and then switch off, and heat up and switch off, every element is not on at the same time, and it's very rare that you would be using every element anywhere. So we can apply diversity to the cooker circuits, and with diversity applied, the current rating comes down to 29.6 amps, and we select our cable to that new value. And also, cookers often have a control switch with a socket on it, which can also add to the overload situation. You want to consider that this is a circuit that can be overloaded, and use the rating of the protective device rather than the design current in your calculations. So we can apply diversity to reduce the current carrying capacity of the cable we need, but we've got to consider, is that cable going through any insulation? Are there any correction factors that need to go on it? So cooker circuits are best run clip direct. So these are the figures for that circuit, 13.5 kilowatts, which equals 58.69 amps. And with diversity applied, the current rating comes down to 29.6 amps. So we need an MCB which is larger than this. So the next size up will be a 32 amp MCB. Now this is a circuit that can be overloaded, so we're going to use IN for our correction factors to get IT. In this simple example, we've got no correction factors, so our IT is 32 amps. So in the tables 4D2A or 4D5 in the clip direct section, it will suggest a 4mm square cable which has a current carrying capacity of 36 amps. We check for the volt drop factor in table 4D2B. In 4D5 also has the volt drop factor as well. And for 4mm square cable, that's 11. So 11 times 29.6 times 20 divided by 1000 gives us a max volt drop of 6.5 volts. So 4mm square cable will be adequate for this cooker, but I know that a lot of people will still put on a 6mm cable. It's just habit and what people do. Cookers, they put it on 6mm cable. So we've got good coordination there. IB, IN, IZ, 29.6, 32, 36. Another check is I2, the current causing operation of the protective device, is less than or equal to 1.45 times IZ. Protective device is 32 amps times 1.45 gives us a value of 46.4, and IZ 1.45 times 36, our IZ, gives us 52.2. Therefore I2 is less than IZ. And if we do get a fault situation which causes an overload on the cable, we know the cable can handle that overload situation until the protective device operates, which we know should be less than an hour if it's put in 1.45 times its rated current. We're almost 50 minutes into this video now, and I think that's enough for anybody. But I still want to talk more about socket circuits, radial circuits and ring final circuits. And I also want to talk about thermal withstand and the adiabatic equation. But I think I'll save that for another video. I hope you found this of some use. Thanks for watching.